A 100-liter vat contains 30% alcohol by volume. Beer, which has 6% alcohol by volume, is being poured into the vat at a rate of 10 liters per minute. At the same time, 10 liters per minute is being drained from the vat. We have two questions. After 10 minutes, what is the amount of alcohol? And also, after 10 minutes, what is the rate of change of the volume of alcohol? Now, let's put out the givens first. We said here that there is a 100-liter vat and it has 30% of alcohol by volume. What that means is that uh of the 100 liters solution that we have, 30% of it is alcohol. So in the 100-liter vat, the 30% alcohol by volume is 30 liters alcohol, which we will describe as L-al to differentiate it from. Now, this is not an easy task to compute, but we can use differential equations to make things easier because what we are looking at is basically change, rate of change. Uh, Beer is being poured into the vat 10 liters per minute. That's rate of change. So it's easier to describe the amount of beer going in or the amount of alcohol going in terms of a differential equation. So let's set up a differential equation now. So d alcohol over dt. This represents the amount of alcohol changing with respect to time. So for example, the change of alcohol in like 3 seconds in is different from the change of alcohol 1 second in. And we can see it here because uh, alcohol is being poured into the vat. At the same time, it's being mixed. This is a mixture problem, so it's an implication that it's perfectly mixed, so there's no weird concentration stuff. But uh, the the other thing is that it's being drained from the vat, the perfectly mixed mixture. So the amount of alcohol being drained from the vat is different each time. It's not a constant 10 liters per minute times 30% alcohol by volume. It's not constantly that. It's changing over time. So we need to calculate for that. So what could be the change in alcohol over time? Well, there's alcohol going in and there's alcohol going out. The alcohol going in is adding to the amount of alcohol within the vat. So it's positive. So this is equal to alcohol in minus alcohol out. And the alcohol going out is being removed. So it's negative or minus. The change in the differential equation means that it's going out. That means it's negative. All right. So this is the simplified version of the differential equation. dA over dt equals A in minus A out. But we need values for A in and A out. In order to do that, in these kinds of mixture problems, there is usually a this guideline. So alcohol or any substance really, this could be salt, alcohol. Those two examples are usually the two most common ones that I see in books and on the internet. And this is equal to volume times the concentration, the flowing concentration. So let's look at the problem. Going in, there's 10 liters per minute of uh, beer going in, which is 6% of alcohol by volume. So going in, we have the volume, which is 10 liters per minute, and the concentration, which is 6% alcohol by volume. 6% is 0.06, and then liters alcohol per liter of the solution. And we can use dimensional analysis to essentially cancel out the liters. We get 0.6. 10 times 0.06 is 0.6. I checked. Liters alcohol per minute. So that's the rate of alcohol going in. How about the rate of alcohol going out? So this is a bit trickier because the amount of alcohol within the vat changes, and that's what it's depending on because 10 liters of alcohol is being drained from the vat, right? So we need to know the volume first. So 10 liters per minute, that's given. What about the concentration? Well, we're given the concentration of the vat, which we presume is the amount of beer going out of the vat. So, uh, the concentration is let's have the units first. Liters alcohol per liter here. So let's have the total of 100 liters here. All right, and the amount of alcohol going out is changing, right? So, it is A essentially the amount of alcohol within the vat divided by the total amount of the solution. That is the concentration of alcohol at one time. And the concentration times the volume is uh, the outgoing concentration. So cancel out the units, we get 0.1 liters alcohol per 0.1 A, sorry, liters per alcohol per 100, sorry, per minute. So 0.1 A referring to the amount of alcohol. So let's put that in our differential equation. Honestly, the figuring out how much alcohol goes out is the hardest part of this whole exercise. Over dt equals going in 0.6. Let's ignore the units for now because we know the units. Going out, that's 0.1 A. All right. So you can use your preferred calculation method for this. You can use uh, separable differential equation by doing a fraction and then dividing both sides by this and that. But I would like to use linear differential equation because I can see that transferring this to the other side, we get dA over dt plus 0.1 A equals 0.6, and this is linear. And the linear special integrating factor is just e times the integral of this 0.1, and that's just a constant. So we just multiply it by t in order to get the answer, and that is going to be the uh, special integrating factor, or the SIF. All right, let's multiply it to both sides. E to the 0.1 t times dA over dt plus 0.1 e to the 0.1 t times a equals 0.6 e to the 0.1 t. Okay, so this is a form of basically the product rule as we discussed earlier in the linear differential equations video. And let's not forget that d equals this 0.6 e to the 0.1. All right, integrate both sides with respect to t. The derivative and the integral cancel each other out, leaving us with sorry, e to the 0.1 t a equals 0.6 over 0.1 e to the 0.1 t plus c. I think you'll agree with me. And 0.6 over 0.1, I believe, hold on. I believe if we check the calculator, if you're not sure, you can always check the calculator. And don't worry, the greatest engineers do this too. They check the calculator for 1 plus 1, really. And 0.6 divided by 0.1 is equal to 6. That's equal to 6. Let's go back. So this is 6. E to the 0.1 t plus c. Okay, to isolate A, we have to multiply by e to the negative 0.1 t. We get 6 plus c times e to the negative 0.1 t. All right, so this A is actually A of t, a function of t, since it's alone here now. So if t is 6 plus c times e to the negative 0.1 t, we have our equation that's not a differential equation. We have our general solution. Now we need a specific solution. Remember, all right, remember the original conditions. Let's read again. 30% alcohol by volume 100-liter vat. It was at the initial, this is the initial conditions usually. So let's write this. So 100 liters and then 30% of it is alcohol by volume. There are other types like alcohol by mass, but that's not really important. Alcohol by volume is good. So 100 liters and 30 liters of it is alcohol. Uh, alcohol. All right. So A of 0, which is the initial condition, this is initial. We know this is equal to 30 liters because at the start there was 30% of 100 liters worth of alcohol. So there's 30 liters alcohol in the initial vat. And we can substitute 0 here. 6 plus C times e to the negative 0.1 times 0. That's just e to the 0, which is 1. So C times 1 is 1. C, sorry. So isolating C, you get C equals 24. And that's C. So going back, A of t equals, oh, there it is. 6 plus 24 e to the negative 0.1 t, and that that below me here is the specific solution. Is that the final answer? No. There are two questions we need to fulfill. After 10 minutes, what is the amount of alcohol? And also, after 10 minutes, what is the rate of change in the volume of alcohol? Let's bring both equations together. dA over dt, as we discussed earlier, is zero point 0.6 minus zero point 0.1 alcohol. And A, as we discussed earlier, is 6 plus 24 e to the negative zero point 0.1 t. All right. So what do we do now? We calculate the amount of alcohol 10 minutes later. That's the first one. And then we need to calculate the rate of change of the alcohol within the 10-minute, in the 10-minute mark. And just conveniently, we need A in order to to know what the rate of change in alcohol is. So we need to solve for A. So if we look back, uh, we need A of 10, which is 6 plus 24 e to the negative zero point 0.1 times 10. All right. 0 0.1 and 10 have units together, but we don't really, pay attention to those. All right. I'm going to show my calculator. 6 plus 24 times, this is E in my calculator, negative zero point 0.1 times 10. Okay, there we go. And if I press equals here, we should get the answer. 14.829 liters alcohol within that. So A of 10 is 14.829, or how many liters alcohol. All right. So that's going to be the amount of alcohol in the 10-minute mark. Now we need to find the rate of change in the alcohol. So dA over dt. Let me just uh, so this function on my calculator allows me to store my values as A is just shift and then store value and then press one of the letters so you can get that. And there you go. So I can use letter A for future usage. It's just how we do it. So 0.6 minus 0.1 times 14.829 liters alcohol. The units don't matter anymore. So, but if you track the units, they do matter. So there you go. Okay. So this is going to be 0.6 minus 0.1 A. Since I stored it in A, it should look like this. And coincidentally, I also used A for alcohol. And if I press equals, this will be negative 0. 88, yes, 8829 liters alcohol. Negative 0.8829 liters alcohol per minute. And we use minutes here since our basis was 10 minutes. So there we go. And yeah, I think that's the answer. Why is it negative? It just means that alcohol is leaving the system faster than it enters the system. Now, uh, we can have another query about this. Oh, I forgot to show you the entire thing. Let me just, there we go. So there's the answer. I forgot to show you through the calculator, but there you go. A10 is 14.829 liters alcohol, and the change in alcohol is negative 0.8829 liters alcohol per minute. Now, if you know your limits, what is the limit as a goes to t goes to infinity in this equation? As t goes to infinity, e to the negative infinity goes to zero. So a of infinity, or as it goes on and on, this will eventually approach 6 liters of alcohol. And so maybe in a long time, like 100 years after the thing, and it's still running, you know there's gonna be 6 liters alcohols whereabouts right there. So that's an interesting thing to note about. And if you if you actually look at it, uh, this actually makes sense because beer has 6% alcohol by volume. If the beer completely replaced the original alcohol, 6% of the alcohol by volume times 100 liters is 6 liters of alcohol. So that does make sense. The alcohol and whatnot. So, all right. So that's going to be the answers. 14.829 liters alcohol and negative 0.8829 liters alcohol per minute. And this is only one case if the amount of alcohol doesn't really change, or the total amount of the solution doesn't change. There's other cases if it rises or if it falls, and I'll cover that in a future topic, maybe in a longer video. That's all for now. I'll see you later, Xanderheads.